Hello, everybody. I hope you can hear me loud and clear, and I hope everybody is having a wonderful morning, afternoon, evening, even some night. I know that we do have some individuals that are across the pond, maybe in the Australia region. Hope you guys are having a fantastic evening, and thank you for joining us today. I'm Amelia Thompson, your host of the Würth Elektronik webinars, and joining me is Stefan Schultz. He is a field application engineer across the pond in Germany. Thank you for joining us. Today, Stefan will be presenting Power Inductor Parameters Explained. We have a lot of really great information in today's webinars, but if you have any questions, simply ask them in the questions box and we will get to them at the end. Of course, if we don't get to them, if you think of a question a little bit later, simply reply back to our email. It's webinarteam@we-online.com. Now, because you registered for today's webinar, you're going to automatically get the video on demand. It should be coming out within the next week or so. And that video on demand will send you directly to our YouTube page or to our video center at we-online.com. Of course, don't forget to sign up for our next webinar. It's coming up next week on October 11th. It is Shielding a Practical Approach. You can register online at www.we-online.com/webinars. Now I'm going to hand it over to Stefan Schultz as he presents Power Inductor Parameters Explained, partnered with Digi Key Electronics.
Yes, thank you, Emil, for the introduction. So welcome also from my side, from Germany. And today we will talk about the power inductor parameters and how they are derived, what are the special, how to read them in data sheets, for example. And later we'll also show an example, a live example using our REDEXPERT tool, how to select a power inductor for a DC-DC converter. This will be today's content of the presentation. So first I will speak about some differences in core materials, which we usually use for our products, and specifically for power inductors, and some of them are also used for power transformers. Then I will show you some core shapes, principal core shapes, and where you can find the air gap. And you always need an air gap in such components to store the energy. Then we will speak about the main parameters. So, for example, rated current and rated voltage. Then I will say something about inductor losses and how they are derived for our products. So the measurement procedure which we use normally. And as I already said, then the last part will consist of inductor selection process using the REDEXPERT tool. So let's start with some core materials. I have categorized them according to the switching frequency of the converter. So as you see here, the scaling goes up to 30 megahertz, which is nowadays not really found in ICs, which are specifically designed for DC-DC power converters. But we can already find frequencies up to 10 megahertz, for example. So usually we deal with some 1 or 2 megahertz maximum. Most of them work on this frequency range. And for those switching frequency ranges, different core materials are useful. Actually, they are not really limited, but of course, the core losses of the materials, they increase with increasing frequency. And so we have different material mixtures used for different frequency ranges. So the first one here, which is named Superflux, it's a brand name from Würth Elektronik, so it's not really found everywhere on the market. It's basically based on an iron mixture or iron oxide with some additional content of nickel oxide and zinc oxide. So, but the most highest content is from iron oxide. So, iron has good conductivity, and so we create core losses due to eddy currents. That's why the frequency range of such material is limited to about 1 megahertz. The next one, WE Perm, is also a brand which uses or is mainly based on manganese zinc material, but with a higher content of iron oxide. Then we have the so-called sintered ferrite materials, or hard soft saturation, or actually hard saturation, but soft magnetic materials that I wanted to say, manganese zinc and nickel zinc. So these are abbreviations for materials consisting of iron oxide and some additional metal oxides. Manganese zinc has a high electrical conductivity. Nickel zinc is the opposite. It's nearly insulating material. Then we have the iron powder cores and hyperflux materials. Hyperflux is kind of an alloy, which is quite a modern material. And there we can go up to higher frequencies above about 5 megahertz. And the newest and most modern materials are the iron alloys. So they are based on iron together with some carbon and silicon content. And with those materials, you can go really high in switching frequency. So also the nickel zinc belongs to this category because nickel zinc, as I said, it's a very bad conductor, electric conductor. So eddy current losses only rise at very, very high frequencies. Without going into much detail, I've listed here the content of different families, different match codes, we say, from our portfolio. So these are most very popular series like the PD or the TPC and the HCM series, which is a flat wire power inductor for higher current. And all of them consist of iron oxide. This is a blue bar here, indicating the content of Fe2O3. So this is the content for every mixture. And then there are some additional metal oxides like zinc. It's also everywhere inside the material, inside the core, and the nickel zinc or manganese zinc as additional permeability to create a higher permeability, for example, in order to reduce the number of turns which you need to create a certain inductance value. So let's look at some principal core shapes. The easiest winding structure is a so-called solenoid or cylindrically wound wire, which you see here on the left side, with a cylindrical rod core inside. Of course, the rod core leads to a focusing of the magnetic field inside the winding, but the drawback of such a structure is that it has a relatively wide and large air gap, because air gap is a surrounding space around the inductor, and so there's a large stray field around that component. So basically no shielding effect. You can increase the shielding effect by putting the rod core inside a ferrite housing, ferrite core housing, which is seen here on the right side. It's the so-called shielded rod core. So 5 sides of that cube, you can say, are magnetically shielded, and only the bottom side is open. And here we also find an air gap where the central core is glued into the cube, into the ferrite cube. On the next page, we see the more common shapes, the so-called drum core shapes, either unshielded, like seen on the left side, or the shielded versions here in the center, or like a THT or the THT component with solder pins, and the shielded version using this gap here on the top, which consists of ferrite material. So the drum core is in most cases vertically oriented. And when we have for the open version or unshielded version, we have a large air gap also here on the side. Some components, the magnetic field on the top is quite low, but still it's existing there. And you can reduce the near field, magnetic field, by adding a magnetic shield ring, which is here on the outside. and the air gap we find usually then as a circumference here on the top and bottom side of the component. And similar here for the shielded version, but with an additional top cover. So there are several air gaps here inside. And then we come to the flat wire core shapes. On the left side, the so-called pod core. It's magnetically shielded core shape. Only the windows here on the side, on left and right side, where the winding is seen, it's kind of unshielded. And the air gap is here in the center leg of this pod core. So it's grinded inside. And same we find here for the PQ core shape. Also, the air gap is here grinded into the center leg. So the fringe field, or stray field, is reduced to a minimum for those components. And on the right side, we have the block core. So in principle, we have two blocks made of ferrite material. And the bottom core is then has this flat wire winding here, but it's actually only one turn, which is used here on inside, and then the top core is glued onto the bottom one. And so that a small, very tiny air gap is created. And then we have the versions with the distributed air gap. So the historic shape, the toroid shape, toroidal core, which is still on the market and still used, but because it consists normally of iron powder mixtures, the usable frequency range is limited to some 100 kilohertz. And usually it takes a lot of space on your PCB, depending on the inductance, of course. So in order to avoid and to create a compact core, compact inductor, those smaller materials based on iron alloys are created. And for example, this version here, which you see, is completely shielded. So the internal winding is completely surrounded by ferrite material. In this case, the iron alloy material with a distributed air gap. So when it comes to shielding, those components are the best. So let's see what main parameters we find for power inductors. First, the rated current. The rated current is always based on a certain self-heating of the coil with respect to or related to the ambient temperature around the inductor. So for example, if I apply a current of 1.13 amps to the winding, it's a DC current, and I measure the self-heating after a while, after some minutes of waiting time, then I can measure 40 Kelvin more or higher temperature related or with respect to the ambient temperature. So if it's 20 degrees Celsius in the room, then plus 40 Kelvin makes 60 degrees Celsius as a surface temperature of the inductor. And this is always given as a maximum. So this is a maximum self-heating of 40 Kelvin. But if you plot the self-heating curve for different current values, then you get this quadratic shape or function, because the power loss is directly proportional to the square of the current. So I squared times R DC. This is a power loss in watts. So we always find this shape for every inductor. Here I've indicated the 40 Kelvin test condition, or actually the definition for the rated current, and the reading here on the horizontal axis, 1.13 amps for this 33 microhenry inductor. If I would define 20 Kelvin only for the self-heating, then the rated current would be only 0.8 amps. So now it's interesting how we determine usually, or how every manufacturer determines the rated current for his components. And I would say the old or the previous standard which we used is the IEC 60512-5-2, which was actually not for power inductors or wire wound components, but for connectors. So connectors for electronic equipment, current carrying capacity tests, they are defined in this standard, and it was reused for power inductors. So those components were soldered on a PCB, which has those dimensions usually, FR4 material and a thickness of 1.5 millimeters, and a copper thickness of only 35 micrometers. And the trace width was equal to the solder pad width, the recommended solder pad width. Everything was put then into a wooden box, like seen here on the left side, where a thermal camera looks through the ceiling and measures the temperature rise when the box is closed. Then step by step, the current is increased, and the equilibrium is then reached at a certain time, after a certain time, and then the current value is fixed, and the temperature also was written into the diagram. But since 2 years, a new international standard is existing, is IEC 62024-2, and it's explicitly defined for high-frequency inductive components, and the part 2 deals with the rated current measurement procedure. And in this standard, there are 4 different test boards defined, A to D. Those test boards need to be placed also in a square box, cubic box, and measured with a FLIR camera, forward-looking infrared. And as an example, I've shown here the board geometry for standard inductors, which is a class A. So in red, this is a solder area. Gray, light gray areas are FR4, so the base material of the PCB. Blue are the connection points, and gray are the copper traces or copper areas. And depending on the rated current, the trace width is defined in this table. You can see here on the right side. This is for standard inductors. I would say that low current or normal current inductors, but for high current inductors, which usually heat up more, some other test boards are defined. So like indicated here on the left side, the class C and the class D on the right side. Now you may argue that there are quite large copper areas, the gray area here, or also here the complete copper area can be used for soldering the component onto it. But it's still not realistic, but we are nearer to the reality on an actual PCB in your application. But at least it's some defined standard which everyone can use, and then the rated current values are more comparable with each other. So we also use this. Also, you can see here the trace thickness is 1 millimeter. This is very unusual for a real PCB, but it's much better anyway compared to the previous so-called component manufacturer standards, which everyone has had its own, where sometimes copper blocks were used for soldering the component onto it. And of course, the more copper, the higher the drainage of heat into the PCB. So we previously used this the test board, which is shown here on this slide. So it's still the so-called legacy board, which we refer to. And but we also use now the new standard test boards, and we have defined a new so-called performance rated current. We name it this way. It's not standardized, but we name it performance rated current, and shows us also in the data sheet. So at least for the high current inductors, it's already finished, and the other component series will follow. They just need to be measured. So in this in the data sheet, then it's mentioned what class, what test board, in this case it's class D, was used for this component. Then there's an application note, which I have linked here on this page, where you can read in more detail what are the differences for different setups, different configurations of the boards, and the different definitions of the rated current. So, for example, we have used the legacy board, which is the blue curve here. And for a definition of 40 Kelvin self-heating, the rated current would be 3.4 amps. This point A here. If we would have used 5mm wide traces, then the component gets a bit warmer for the same current, so it's around 49 Kelvin. But if I use a 5mm trace width, but with forced convection, this is a dashed blue curve here, then of course the component is cooled down due to convection much more. And so it could be more realistic if you use a heatsink, for example, and the forced convection airflow, then of course the component stays much cooler. And the red curve here shows the new test board, a new definition for the performance rated current with the same self-heating of 40 kelvins. On the right side, there's an inductance drop. It's the second vertical axis, which the gray curve here belongs to. So this is the inductance drop, the so-called saturation effect, and we will speak about saturation just now. So saturation current, the next value which you find in the datasheet as a usual parameter. The saturation current is in no way related to the rated current. So it can be either higher, can be also lower. The saturation current is purely defined on a specific drop of the inductance. So the so-called saturation effect, each third material shows this effect, regardlessly if there's an air gap or not. Of course, if there is an air gap, the effect is minimized. So it's still, or again, a DC current. And you see in the test conditions that, for example, for this part, which I have selected here, the inductance drop is defined as 10% in relation to the nominal value, which is 33 microhenries. Again, this is only one operating point on the curve, saturation curve, which is shown here in orange. So the operation point would be here for the definition of 10% inductance drop at 1.46 amps. If I would define 30% inductance drop for the same component, then I would be on this part of the curve, and then the saturation curve would be higher. But we try to not to be working on this slopey part of the curve because if you change the current slightly higher or lower, then there's a big shift in the inductance value, a big deviation, and this could lead to not functioning of the application in the end. And there's an additional effect which I will speak about in a minute. It's a temperature effect, which needs to be taken into account. Determining the saturation current is quite easy. You only need a DC generator, and which is shown here in an LCR meter with a 4-wire measurement. Then it's quite simple to step through each current value and measure the inductance. When we speak about saturation behavior, there's a difference between the hard and soft saturation. So I have shown here 4 components, different series. 2 of them show a soft behavior. It's the LHMI series and the HCI, blue and red and green curve. So what does it mean, soft saturation? That means that the inductance drops relatively constantly with increasing current. So there's no real constant value or current range where the inductance stays constant. But from the beginning, it's going down. And the hard saturation in difference for the PD and for the TI, for example, they have for a certain current range, the inductance value stays constant, but then drops more rapidly into saturation. This is typical for the so-called sintered ferrite materials like nickel zinc and manganese zinc. And the higher the content of iron oxide in the core material, the softer the saturation is. If I also consider the temperature effect, that's specifically important for hard saturation behavior materials, so like the PD, which I have shown here. This is from minus 50 degrees Celsius up to 125 degrees measured, and there's a large deviation in the inductance in the saturation current. So also the nominal value of the inductance rises with rising temperature, increasing temperature, but the more dramatic effect we see here. So for higher temperatures, the saturation current is much lower. So this needs to be taken into account when selecting an inductor for real-world applications. The next parameter is the rated voltage. It's not found everywhere in our datasheets, but we are still working on it to also give this information in the datasheet. Of course, the rated voltage is a DC voltage that can be applied permanently across the inductor terminals without any damage. And of course, it depends on the pad or pin distance and the core material's electrical conductivity. The higher the conductivity, for example, if we speak about manganese zinc or iron alloy mixtures, if they have a high conductivity, and there usually the rated voltage is lower, can be down to 40 volts only. If you go too high with the voltage, then even if it's only short-term applying of the voltage, there is a risk of leakage currents or creepage currents across the surface of the inductor. So this needs to be taken into account additionally. And the last parameter I would like to mention is so-called self-resonant frequency, which is also given in the datasheet as a typical value. So if we plot the impedance of the component versus frequency, then there's an impedance maximum at a certain frequency, which is a resonant frequency. And above this frequency, the component behaves more and more capacitively. So due to its parasitic winding capacitance. This is mainly important if you want to use the inductor for filtering application. So if you want to define an LC low pass filter corner frequency, for example, it's important to stay in the frequency range of filtering where the inductor actually behaves as an inductor and not as a capacitor. Then next, let's speak about the inductor losses. So inductor losses in general can be split into different components. So in general, we have the DC losses and the AC losses. The DC losses, of course, are, just see that it's not the English version. I need to translate it again. But the winding losses can be split into the DC losses and AC losses due to skin and proximity effect. And the core losses are mainly due to hysteresis losses, due to the excitation of the core material with a sinusoidal signal, and the eddy current losses. And all of them, summarized, gives the overall total losses of an inductor. And in order to determine those losses, specific measurement devices exist on the market. And which is an example is seen here on the right side. This resembles an actual power inductor or power converter device with an amplifier inside. And with that, you can measure the inductor under real application conditions. So the inductor current is triangular shaped, like seen here. You can vary the frequency with a wide frequency up from kilohertz to 10 megahertz range. The voltage is variable and the current through the inductor is variable. Also, the duty cycle can be adjusted, and ambient temperature up to 225 degrees Celsius. So this is a wide parameter range which can be covered. And we have measured all of our components with this device. And from that, we have built a loss model, which is then implemented into our REDEXPERT tool. So what is the advantage of our own model? Yeah, it has a real operating condition, and that means in the hysteresis curve, which is in here, we are working at the real operating point. So in the first sector here of the curve, we have this so-called minor hysteresis loop here, which is cycled through, and we have this triangular shaped current with an average value here in the center. And compared to the Steinmetz model, which maybe you also know, it's existing for several decades already. But the Steinmetz model always has a sinusoidal excitation and without any DC bias. There are additional advanced Steinmetz models, which also take into account the DC bias effect and variable frequency and excitation amplitude. But the basic model is very simple and does not take this into account. And then only the core losses are considered, not the winding losses. And because we have measured the whole inductor, not only the toroidal core, we can say that we have a combination of all losses. In the end, they can be separated, but not fully. Only the DC losses can be subtracted from the overall losses. And the AC losses will remain. So due to skin proximity effect and the core losses. So the last chapter regards the inductor selection. And before I show the live demonstration using the REDEXPERT tool, I will show you the example which I have selected. It's an asynchronous buck converter with a nominal input voltage of 24 volts, output voltage of 5 volts, a diode voltage drop of 0.3 volts, output current is 2 amps, and the ripple factor, recurrent factor for the inductor, I have selected 0.2 or 20%. Switching frequency should be 500 kilohertz, and the ambient temperature is 90 degrees Celsius. Using those given parameters, it's possible to calculate different derived parameters, like for example the duty cycle. It's roughly 18%. And the turn-on time can be calculated 350 nanoseconds. And using the duty cycle and the output voltage and diode drop, as well as ripple current and the switching frequency, we can calculate the optimal inductance value, which is roughly 22 microhenries. And also important to know is the peak inductor current, because it needs to be related to the saturation current. We want to try to avoid the inductor going into saturation. So this is a nominal output current plus half of the ripple current. In this case would be 2.2 amps. Those values I will switch to the REDEXPERT tool. Should be visible. So maybe you've seen this tool already. It has a slightly new view since 2 or 3 weeks, but only the start page is different. The module here for power inductors is still the same. So it's a complete list of all inductors, which we can find here in our portfolio. And on the left side here, you see that there are different tools for calculating losses, for example, or for calculating the optimal inductance for buck, boost, or SEPI converters. So of course, we will use the buck converter design tool. And here are some predefined values already given, but of course we can edit them. So let's type in the values which we have seen in the presentation before. Maximum input voltage 20 to 30 volts, non-synchronous or asynchronous. That's already given here, 2 amps, 5 volts at the output, 500 kilohertz is also okay. Inductor ripple current factor should be 20%. And the diode voltage drop 0.3 volts. Then if you have typed in all values, then click on update, and then the list should update. Yep, that's should be done now. So as you can read here on the top right corner, 58 items. That means 58 inductors are still possible to be used in this application. But we can make some more adjustments. For example, if we click here on the inductance versus DC current chart on this drop-down list here, we can adjust the ambient temperature, for example, to 90 degrees. This was our goal. And then we see the real saturation behavior at 90 degrees Celsius ambient temperature. Now we can adjust here this slider to the maximum inductor current, the peak inductor current, which we have calculated before. It's 2.2 amps. Can also be read from the details. If you click here on details, then here on the top left, you see the maximum inductor current calculated. Also, the optimum value is indicated here. So if we set the slider to 2.2 amps, and we go into the table here on the top, then there's already a filter for the inductance value was set, but it's possible to modify this filter and say we want to have at 90 degrees Celsius and 2.2 amps, we want to have a minimum value of 22 microhenries. The upper limit could be, it's still not updating correctly. Now it should be, yes. Yeah, there's a slight bug here I experienced today, that the current is always reset to 2 amps. But nevertheless, it should work during the next days after fixing this. So here we still have the list, but now it has increased. It should decrease. So there's a small bug here. But we find now inductors which have a minimum value of 22 microhenries at this operating condition. So all of those components fulfill this criteria. But of course, it's maybe we should limit this to 25 microhenries, and not so many components are visible. Yeah, only 17 items now are left. So of course, still a large selection possible, but of course, the tool also calculates the total losses. So this is a column here, P total, and if it's possible to sort them, ascending or descending order. So if I click on the first component here, which has the lowest, or actually this one has the lowest total losses, only 21 milliwatts. But of course, if you look at the component, it's a quite large one, 2818 size. So it's a flat wire PQ core inductor. And of course, flat wire, stays very cool at 2 amps. It's possible to add additional filters. For example, shielded can decrease the number of components to only shielded ones. Or assembling technology, for example, if you prefer only SMT components, then you can select SMT in this column. Yeah, still 41 items left, but it's possible, for example, to limit the height to 5 millimeters. For example, if you are limited in height in your application, or you're limited in footprint, it's also possible to adjust here the length and the width column. So it's possible always to reduce the number of inductors which can be selected from. and then choose the one which has the best efficiency or the lowest total losses. And of course, it's possible to compare those components if you click here on More button on the right side, Fill Tray, and then all of those 7 items which are left are compared with each other. So at a glance, you see all saturation curves or components. So we have here 3 components which show soft saturation behavior, and the remaining 4 components have a hard saturation. And here also is a self-heating curves. So for example, the brown curve here, brown component, is a HMI, but quite small in size, only 7 by 7 by 5 millimeters in volume. This has the highest self-heating for a given current, whereas the orange one here, the HCI, flat wire inductor, shows the lowest self-heating. Yeah, this was an example, and I will switch back to the presentation now, because I have summarized all the different steps which I have just shown before here in the presentation, and you will get the presentations afterward, as my colleague has mentioned. So you can always read how to work and how to select power inductors for your application using the REDEXPERT tool. That was all from my side. Thank you very much for listening. And now we'll come to the question and answer section.
Thank you very much for presenting, Stefan. We do have a few questions coming on in. One of the more popular ones is the presentation going to be available? And yes, we will make the slides available to you after today's webinar. Our first question coming on in is, does Würth Elektronik have power inductors with a rated voltage greater than 120 volts?
Yes, we have the so-called high voltage series. Maybe it's also visible here. Yeah, it's a German one, but I think you see this. There are 3 series which have a rated voltage of 400 volts. This is the absolute limit we have in our portfolio. Of course, it could be, you can think of inductors going higher in voltage, and in the future it will be more important. But those are suitable for to be used as a filter inductor, for example, for the mains power supply. So at 230 volts RMS, and but also for DC-DC power supplies. So if you want to avoid, or if you fear that there could be a sparks or occurring due to increased voltage across inductors, then those components are suitable.
Excellent, thank you. Our next question coming on in, do core materials with soft saturation have temperature dependency?
Yes, they have, but a much smaller dependency compared to the hard saturation component, which I have showed in the presentation, the PD series nickel zinc. No, they still have some minor effect, but it's nearly neglectable. So let's skip through the different questions. Some of them are related only to the presentation. Yeah, maybe this one regarding the dot. Do you see it, Amelia? Should I read it, or will you read?
It's just coming on in here. Our next question here, what is the dot on the SMD inductor in a previous slide? I believe that was around slide 16 or 17. I was just trying to find it.
Can go back. Is that one? Yeah, this is visible here on near the marking. And another slide. We are not. Yeah, it's also visible here. Yeah, this marking dot on the top surface this indicates the start of winding. So this, we always recommend to put this dot, or the side of this dot, oriented to the switch node of the power converter. So this can have an effect on the near field radiation, because the high or the steepest slope for current and voltage occurs normally at the switch node, and specifically for inductors which have a higher inductance value, there are sometimes 2 or even 3 winding layers on top of each other. So that means that the outer layers shield the inner ones, and it's possible to show the start of the winding here on the left side on this example. If you see it, this here where the shortest connection between the terminal, the solder pad, and the inner core, the central core here. This is the start of the winding, and then it goes up and sometimes down and up and down again. But we always need to go on the other side down back to the second terminal, and so we can have the shielding effect of the outer layers. That's why it's recommended to put the marking, the dot, to the switch node.
Thank you for that explanation. I've been working with the company for many years now, and every now and then, just the little things like that, I just tend to forget about them. So hearing that explanation definitely helps. Our next question here: do you have a similar tool for power capacitors?
Not yet. The REDEXPERT already includes power capacitors. So all types, aluminum polymer, aluminum electrolytic, and ceramic types. But there's only a lifetime calculator included, but not, I would say, not a calculation tool for capacitors. So this will be in a future version. I'm sure that someone already had the idea to implement this, but it's not yet existing.
And REDEXPERT, as you mentioned, is constantly updating. It is constantly changing. So I think within the last year or so, they've added several new parameters and tools to the program. So I expect capacitors to be there power capacitors to be there very soon. We're winding down on time, but we do have time for a couple more questions here. Can you explain the importance of self-heating in an inductor again?
Yes, maybe using this slide. I did not mention the derating of the current, because every inductor has a certain maximum operating temperature, which is usually 125 or 150 degrees Celsius, and this should not be exceeded, at least not for a longer period. For short term, it's possible to overheat, but not for a longer time. That means, depending on the definition of the rated current, for example, 40 kelvins and 125 degrees Celsius maximum temperature for the inductor, it means above 85 degrees Celsius ambient temperature, you need to decrease the current. It's no longer possible to apply the full rated current. So it has to be decreased by a linear derating, which is also given in the data sheet. So in order to avoid overheating of the inductor.
Thank you very much for that explanation. One more question here, and then we'll be done. And again, if your question did not get answered today, then we'll gladly answer it after today's webinar. Just look for that email at webinarteam@we-online.com. Our final question here: can REDEXPERT select based on footprint or package size?
Yes, that's possible. I did not show this, but if you use REDEXPERT and you are a registered user, then that's not so good visibility on the top, but there is a small wheel here. It's actually not visible. Just let me delete some filters. Maybe now it's visible here, this small cog. If you click on it and select columns, there are different additional, I need to change the view. different additional columns selectable. So if you scroll down here, there's, for example, one footprint which you can activate, or maybe also volume. So if you have selected those, then the additional columns appear, and you can read here directly the volume of the inductor or the footprint area in square millimeters. So if in a standard view, it's not visible, those columns, but you can adjust them, and it will also be saved for the next session. You open REDEXPERT.
In short, REDEXPERT can do just about anything but order your groceries. And who knows, maybe in the future we'll have a partnership with Uber Eats. But for now, we're going to stick to our power inductors and flyback transformers and anything else that REDEXPERT can do. Stefan, thank you so much for presenting today's webinar. I think that we've had a lot of really good conversations, especially going on in the Q&A. And again, if you have more questions, we will get to them. Just look for that email at webinarteam@we-online.com. And if you have any questions, you can always reply back to that same email. You will be receiving the video on demand within the next week. Again, just look for that link in your email. Also, don't forget to listen to the new Würth Elektronik What's Up podcast. Each week, we are turning our webinars into an audio format. You might be seeing it on YouTube. Obviously, it's a podcast, so it's going to be that audio format. That is the Würth Elektronik What's Up podcast. This week's episode is actually a webinar from July. It's Transformers. What characteristics are important to you? And that'll go live Thursday at 12 p.m. Central. You can listen to the What's Up podcast on Spotify, iTunes, Google Podcasts, all major podcast streaming networks. Again, that's the Würth Elektronik What's Up podcast. Join us for our next webinar. It is next Tuesday. It's Shielding, a Practical Approach on October 11th. Register online at www.we-online.com/webinars. I'm Amelia Thompson. Thank you for joining us, and I hope to see you soon.
Thanks also from my side, and see you soon.